This section talks about representation of functions as power series. The main goal is to represent certain functions as sums of power series. The main tool is by manipulating geometric series or by differentiating or integrating such series, we can obtain power series representation of these functions. The basic result that we're going to use in this section is the following. The sum of the geometric series x to the power n and from 0 to infinity is equal to 1 over 1 minus x. Now, to prove this result, we can start from the right hand side, x to the power n, and from 0 to infinity. This series can be expanded as 1 plus x squared plus x cubed, and then we look at these terms of the right hand side. We notice that this is geometric series where a, the first term, is 1 and the ratio is x over 1 or x squared over x. We divide each term by the previous term, so we get x, so the ratio is x. And now we know that since r, absolute value of r is absolute value of x, but absolute value of x is less than 1, that means this is convergent. Now, since it's convergent, we can find the sum. The sum is a over 1 minus r, but a is 1 and r is x, so we obtain the function 1 over 1 minus x. So this result will be used extensively here in this section to find representations of some functions as power series. So let's start with the first problem. We want to express the function 1 over 1 plus x squared as sum of power series and then find the interval of convergence. So we start with what we know. We know that 1 over 1 minus x is equal to the series x to the power n and from 0 to infinity. Now we want to get this function. So to get this function, we write it here, 1 over 1 plus x squared, and then we try to write it in this form, in the left-hand side form. So we can write 1 over 1 minus x squared. And now by looking at this expression, it looks in this form. So that means we can compare it with the right-hand side and or compare it with the left-hand side to get the right-hand side. We can write it as a series. So from n equals 0 to infinity. Now instead of x here, we have negative x squared. So we plug negative x squared here, and we still have the power n here. And then we can simplify more. The series from n equals 0 to infinity of negative 1 to the power n times x to the power 2n. Now, if we want to expand this to find some terms of this series, we plug 0 to get 1, then plug 1 to get negative x squared, then plug 2 to get x to the 4th, then negative x to the 6th, plus So this is the series that we obtain. Now this series is convergent if the absolute value of this, of x to the power 2, or the absolute value of this, by comparing this series with this series, as you can see, the absolute value of x is less than 1, and here we have x squared. So, or negative x squared. The absolute value of negative x squared is less than 1, and that's equivalent to absolute value of x squared less than 1. and then we try to find an interval where x belongs to. So this series is convergent if this is true. So we expand this, we write this as x squared less than 1, and then bring this to the left hand side, you get x squared minus 1 less than 0, and then study the left hand side. So we have x squared minus 1 equals 0, and then try to find the zeros of this. The zeros are plus or minus 1. Put them on the number line and study the sign of the left hand side. So if we choose a value greater than 1, like 2, plug it here, you get positive value. Choose 0 between -1 and 1, you get negative. Choose -2, for example, less than -1, you get positive. So this is true. This inequality is, this expression is less than zero in this interval. So that means the series is convergent on the interval -1 to 1. This is the interval of convergence. Or we can write absolute value of x is less than 1. So this is the interval of convergence. And we could find the representation of that function. So 1 over 1 plus x squared can be written as the series of -1 to the power n, x to the power 2n, and this is power series. Another example, we want to find the power series representation of the function, for the function 1 over x plus 2. So we start with this function 1 over x plus 2, and we try to write it in the form 1 over 1 minus x. So we have 2 here, we don't have 1, so we can take 2 as a common factor, and we are left with 1 plus x over 2, and this is 1/2 times 1 over 1 minus negative x over 2. And as you can see, compare this to this, you can find that the expression here is written in this form. So we have 1/2 times the series that represents this is n from 0 to infinity of negative x over 2 raised to power n, and then we have 1/2 times the series -1 to the power n times x over 2 to the power n, n from 0 to infinity. So we could find some representation, and here n still from 0 to infinity. Now this geometric series is, actually we can insert 2 here, so we can write it this way: series n from 0 to infinity, -1 to the power n, x to the power n over 2. Here we have 2 to the power n, and we have 2 times 2 to the power n is 2 to the power n plus 1. So this is a representation of 1 over the function f of x equals 1 over 1 plus x plus 2. Now after that, if we want to determine the interval of convergence, we just take this expression here, which is raised to the power n, and we want the absolute value of x over 2 to be less than 1, and then we get absolute value of x is less than 2, and that means, actually here this can be written without using absolute value notation as x between -2 and 2. So this is the interval of convergence. Interval of convergence. And the radius of convergence is 2. So this is r, radius of convergence. And as you can see, you can use this x over 2, or you can use this with the negative sign, but since we have absolute value, we don't need to worry about the negative sign. Let's take another example. We want to find a power series representation of the function f of x equals x cubed over x plus 2. So we start with what is given. So the function is x cubed over x plus 2. We can write this as x cubed times, our goal is to write it in this form, 1 over 1 minus x. So this is x cubed times 1 over x plus 2. And then we have a similar situation as in the previous example. So we can write 2 plus x, and then we take 2 as a common factor, and we are left with 1 plus x over 2. And then we can write this as 1 minus negative x over 2. We have similar situation as before. So this is x cubed over 2 times the series n from 0 to infinity. So this is written on this form, but this form is x to the series x to the power n. So instead of x here, we have negative x over 2. So we write it as negative x over 2 to the power n, and that means we have x cubed over 2 series n from 0 to infinity, negative 1 to the power n, then x cubed over xn, x to the power n over 2 to the power n, and then we can insert this expression inside, or write it inside the series. It gives the series negative 1 to the power n, x to the power n plus 3 over 2 to the power n plus 1. So this is the power series representation of the function x cubed over x plus 2. Now, if we want to find the radius of convergence, the radius of convergence is the same as the previous example. So we have this is convergent if the absolute value of negative x over 2 is less than 1, and that means the absolute value of x less than 2. That means x is between negative 2 and 2. So the interval is negative 2 and 2. So the series is convergent if x belongs to this interval. And as before, the radius of convergence is 2. Now, sometimes it's not easy to write the function directly or by just manipulating the function to write it as a power series, or manipulating the power series to represent the function, as we did in the previous examples. The 3 examples, we started with the function and tried to write it in the form of our geometric series. But sometimes this is impossible or hard to be done. So what should we do in this case? In this case, we use what's called differentiation and integration of power series. So differentiation and integration of power series. So if we have, now we need to know that the sum of power series of that's written as f of x equals, this is the general form of the power series, cn x minus 1 and minus 8 to the power n, whose domain is the interval of the convergence, or the interval of the convergence. So how to differentiate this? This is the power series, the general form of the power series. So if we want to find the derivative of this, we are assuming here that this is differentiable, and hence it's continuous, actually continuous, and it's defined on the interval a minus r and a plus r, the interval of convergence. And here the derivative of this. How to differentiate this? We differentiate this as if it's any function, known function. So we have the series here. What is derivative of this inner function? Cn is constant. X minus a to the power n is differentiated by using power rule. So the power is n. The power is n, and then we subtract 1 from the power. So this is how we differentiate this, and we, instead of starting from n equals 0, we start from n equals 1. Now, how to integrate? To integrate f of x dx, we just integrate the inner function. So it's the integral of n from 0 to infinity of Cn x minus a to the power n dx, and then we obtain what is the integral of this. Integral of this is Cn x minus a to the power n plus 1 over n plus 1. We just add 1 to the power n from 0 to infinity, plus some constant of integration is c. Now if you want to understand this more, you can expand this series and then integrate each term separately, and then find the sum of these terms, and then try to write them in this compact form. So we need to use these tools to find representation of some functions. So for example, if we have the function f of x equals 1 over 1 minus x all squared, as we can see, it's not easy to compare this to 1 over 1 minus x because of the square here. So how to do this? We need to think of either integration or differentiation, but we know that if we start from the power series, if we start from 1 minus x, which is the sum from n0 to infinity x to the power n, then we can find the derivative. If we find the derivative of this, derivative of the left hand side is 1 over 1 minus x all squared, and the derivative of the right hand side is n times x to the power n minus 1, and here we start from n equals 1. And the reason is that we start from n equals 1 because the series x to the power n has the expansion 1 plus x squared plus x cubed, etc. And then when you differentiate the left hand side, you get nx to the power n minus 1. Differentiate, that means we are differentiating this series. When we differentiate this, we get 0 plus derivative of x is 1 plus derivative of x squared 2x, and so on. So as you can see, this corresponds to n equals 0, and then n equals 1, this n equals 2. But as you can see, the first element, the first term is 0, so that will not affect the sum. So that's why we start from n equals 1 after differentiation. After the differentiation, we start from n equals 1, and that's what we did here. Okay, now we have this, and as you can see, we got the left hand side, the function that we want to obtain the geometric series representation for it. So we can write 1 over 1 minus x to the power 2. If we want to bring this to 0, n equals 0, we need to add 1 to each n inside the series. So we can start from n equals 0 to infinity, but we have to add 1 to each n inside the series. So this is convergent if the absolute value of x is less than 1. So this is r, radius of convergence. Now let's do another problem. We want to find the power series representation of the function f of x equals natural log of 1 plus x. Now, as we can see here, so differentiating is not enough because we can find representation, but we still have derivative here. And then we need another tool. The other tool is the integration. So if we have 1 over 1 plus x, the derivative of this is 1 over 1 minus negative x, and this is the series negative x to the power n from 0 to infinity. And this is convergent if absolute value of negative x is less than 1, or this is equivalent to absolute value of x less than 1. Now we need to get rid of this derivative because this is derivative, not the original function. So in this case we need to integrate. So we integrate both sides. We integrate the left hand side and we integrate the right hand side. The right hand side is this integration of the sum from n equals 0 to infinity of negative x to the power n dx. Now, integrating the right hand side, we can insert the integral here or exchange the sum and integration. And then what is the integral of this function? The integral, before integrating, it's better to write it this way. -1, this is -1 to the power n, then x to the power n dx. It becomes easier to deal with, to integrate this if we write it this way. So this is the sum n from 0 to infinity of the -1 to the power n, because this is constant. Now integral of x to the power n is x to the power n plus 1 over n plus 1, plus the constants of integration is c. So what is the integral of the left hand side? The integral of the left hand side is ln 1 plus x, and that's the function that we want to find representation for it. And as we can see, we obtained some representation, but it's better to find the value of the constant c. So how to find c? To find the value of c, we can take any value of x from the domain. So we can take x equals 0. That gives the left hand side becomes ln of 1 plus 0, and the right hand side sum of, when x is 0, everything here is 0. So 0 plus c, and that means we have natural log of 1 equals c. Natural log of 1 is 0, c is 0, so we don't need to write it here. So we have natural log of 1 plus x is equal to the series n from 0 to infinity, -1 to the power n x to the power n plus 1 over n plus 1 plus 0, so we don't need to write it here. Now, it's sometimes if we can write this as x to the power n, not x plus 1, that's a preferred form. So we can write this as x to the power n by changing those. So if we subtract 1 from n inside the series, we add it to n in the series notation. So that means instead of starting from n equals 0, we start from n equals 1, and then we subtract 1 from each n inside the series. So this becomes n minus 1, this becomes x to the power n over n. And this is convergent if absolute value of x is less than 1. So 1 is the radius of convergence. Now we have another example here. We want to find representation for the function f of x equals tan inverse x. Now to do so, we need to think of first integration, because we can't do this directly. We can't apply the geometric series directly and compare the function with that series. So we need to work on this. If we know that the derivative I mean, we need to work on this using some tools, differentiation and integration. So what is the derivative of tan inverse of x? The derivative of tan inverse of x is 1 over 1 plus x squared. And as you can see, this can be compared to the geometric series that we know, and we obtain the series n from 0 to infinity of negative x squared to the power n, or the series n from 0 to infinity negative 1 to the power n x to the power 2n. And then we want to get rid of this derivative because we have the function f of x, not the derivative of f of x. So to get rid of the derivative, we integrate both sides. To get the integral of this is the integral of 1 over 1 plus x squared dx. This is the left hand side, equals the integral of the right hand side, the series from n equals 0 to infinity negative 1 to the power n x to the power 2n. And then we find the integral of the right hand side. The integral of the right hand side is sum n equals 0 to infinity negative 1 to the power n x to the power 2n plus 1. We add 1 to the power and divide by the new power plus some constant c. Now we try to find the value of c. So to find c, let's take x equals 0. When x equals 0, we have, since the left hand side represents the tan inverse, this is the integral of this is tan inverse of x. Substitute 0, you get tan inverse of 0 equals, this is 0 because x is 0, plus c. Now tan inverse of 0, what is the angle whose tan is 0? It's 0, equals c. That means the value of c equals 0. So we get tan inverse of x equals the series n equals 0 to infinity negative 1 to the power n x to the power 2n plus 1 over 2n plus 1. Now here it's not easy to convert this into n because of the 2 multiplied by n being multiplied by n. That means we don't need to worry about this. We just leave it in this form. But this is convergent if absolute value of x is less than 1. And 1 is the radius of convergence. Now the last example here is that we want to evaluate some integral. We don't want to write the function as a power series, but we want to integrate, and then after integrating we get a power series. So if we ask you to integrate the function 1 plus x to the 7th dx, we can evaluate this as a power series. And this is one of the applications of the power series of this section. So we start with 1 over 1 plus x to the 7. This is the basic function. And this can be written as 1 over 1 minus negative x to the power 7. And using the representation of the basic geometric series, this is the series from n equals 0 to infinity of negative x to the power 7 to the power n. This is series n 0 to infinity negative 1 to the power n times x to the power 7n. Now we apply the integration. So the integral of 1 over 1 plus x to the 7, integrating, we integrate both sides. So we get the integral of the right hand side, and then we interchange the sum and integration. And then we integrate this function. We get the sum n equals 0 to infinity negative 1 to the power n x to the power 7n plus 1. We add 1 to the power of x and divide by the new power plus some constant c. So this is the integral 1 over 1 plus x to the 7 dx. This is the representation of this integral. And since we still have c here, we don't want to substitute some value of x, just find the integral. This is the integral, because when we find indefinite integral, we usually have a value or some constant added to the integral. That constant is called the constant of integration. Now, if we want to expand this, just to show you some terms of this, you get c, this c, plus substitute n equals 0, you get x, because 7 times 0 is 0 plus 1, 1. So we have x times negative 1 to the power 0 is 1. So, and the second one, when we plug n equals 1, we get negative, because negative 1 to the power 1 is negative, and then n is equal to 1 here, we get x to the power 8 over 8. And then substitute n equals 2, you get positive 1 here, and then x to the power 15 over 15, and so on. So this is convergent if the absolute value of x is less than 1. And 1 is the radius of convergence.